Hey everybody. So it's 9:40. I think we're going to go ahead and get started. Welcome to Quarantine Week X and another exciting day of remote lectures. I'm really excited for today because this is actually a topic that I'm very, very much active in right now at our office and also just regionally um, in Northern California. So um, this information is definitely current, like as of yesterday or the week, last week for policy stuff. Before I jump into the lecture, I just want to encourage folks to use the Zoom chat window. If you have questions as we go through, I'll try to answer them. Likewise, if you have a question you don't want to share publicly, feel free to send a private message to your GSI, and you can have those conversations on the side as well. Also, before we get started, just a quick reminder about the announcement that I think went out yesterday on exam logistics. There's a survey that we'd really appreciate for you to complete to give us an idea of anything else that we need to be planning around as we approach final exam. So with that, I think I'm going to get started. So today is really building on what we talked about over the last couple lectures, which is around building codes. So Gail talked about LEED and Living Building Challenge, and I talked a little bit about where the baseline building code Title 24 sets us up. Today is really talking about REACH codes and really talking about going far beyond what the state minimums are to do some rapid decarbonization, which is pretty, for me, pretty exciting. So a little bit of background. In 2018, our governor signed a bill, SB 100, that actually required our electrical grid in California to become carbon neutral by 2045, which is not that far away. It's 25 years from now, which sounds like a lot, but it's not when you talk about trying to transition the entire electrical grid to be carbon free. And then most recently, another executive order trying to move our entire economy to net zero energy. So these two bills actually really spurred a pretty big movement in California and to try to get towards what we consider sort of zero carbon electricity, which then tells us a story about where we want to go with how we use energy in buildings. One of the other big things that happened, and you guys are part of this, is that the UC Office of the President, in their new sustainability policy guidelines, eliminated the option of using new natural gas for space heating or for domestic hot water, which is a really big move. If you think about how many students, how many square feet of buildings are within the UC system, there's a lot of construction happening at each of the campuses, and their policy essentially said no new natural gas, which is amazing, and really is pushing towards this drawdown of the use of natural gas and the carbon associated with it. And then ultra locally, the Bay Area has been a tremendous driver in trying to push towards all electric buildings. And I'm going to explain why in a little bit, but this just gives you an idea of just some of the local cities from Alameda, Berkeley, Davis, Los Gatos, all over Palo Alto, San Jose, that have passed local building codes that are actually stricter than the state code. So the city of Berkeley, if you guys didn't hear, this was back this fall. I helped the city of Berkeley write their new energy code, sort of their stretch goal code, which eliminated natural gas completely from new construction. So city of Berkeley, new buildings, no new natural gas connections, which is a really big change, and was the first city in the country. That happened, and then all of a sudden another 20 cities decided that they didn't want to be caught behind. And so a lot of the cities that are listed there on the left are cities that have adopted either a gas ban or what we call a REACH code. So those are codes that say if you're going to be all electric, you can meet the California code. If you use natural gas, you need to be X% more efficient than the state building code. That was the case for San Jose. So that just passed, their REACH code just passed this fall, also in December. I was there for that too and helped them craft their code as well. So really exciting movement, very much a grassroots movement to try to transition buildings off of natural gas, which for those of you who haven't been in sort of the utility world, natural gas was pushed for a really long time as like the clean alternative. It was like clean natural gas, and it is relatively clean compared to coal, which is awful, but it's actually not a clean energy source. There's a lot of CO2 emissions associated with it, but even more, there's a considerable amount of methane associated with it. We'll talk about that in a second. So all these codes, though, have to get approval from the state before they're allowed to use them. And really exciting news in December and then again in January, all the cities that had applied to use their own REACH codes were approved by the state. So the state has totally decided to get out of the way, and if cities want to be way more aggressive, the state is letting them. So a huge movement around electrification and getting off of natural gas. So that was back in December when the first set of 20 or so cities were okayed. Now we're over 30 cities in California that are going towards some sort of all-electric REACH code or a natural gas ban, which is really exciting. So it's a huge wave, and it reframes how we talk about systems inside buildings. And it reframes the discussion around when we use power and how we use power. And all of this framework, all of these codes are really trying to drive towards lower carbon emissions and trying to eliminate combustion as a source for energy in our buildings. So why is that important? If you've been paying attention to the news at all in the last probably year and a half, 2 years, there's been some really interesting work coming out of vehicle-based chemical sensing. There's been a number of instances where the Google Maps folks have actually installed methane sensors on their vehicles, and they're simultaneously doing GPS tracked methane source detection as they do their mapping exercising, which is really exciting. But it's showing you, the image on the left is actually from Southern California in LA. As they were driving around, those red spikes are actually spikes in detected methane leaks. So we have this massive gas infrastructure underneath our cities, and it's very poorly maintained. A lot of the pipes have corroded, a lot of the valves have corroded. It doesn't take very much to remember San Bruno, which was just a couple of years ago, where we lost an entire neighborhood due to gas explosions. So it's not just the risk of explosion and safety, which is a huge concern, but it's also these undetected methane leaks, because methane is 1,000 times more potent greenhouse gas than CO2. So if you have a little bit of methane leaks, it's equivalent to 1,000 times that amount of CO2 emissions. And what these tests or this mapping exercise was showing was that we're releasing way more methane into the atmosphere than we were aware of, and it's not just at the extraction sites, like in Nevada and the Dakotas, in Texas. It's also through our entire distribution network. That's all pressurized gas in those underground pipes, and they're leaking. The images on the right were some research that was just recently done, where they were actually they used essentially a false or a sensing camera that can, instead of looking at light, it's looking for gas. So these are false color images representing the gas sensing. And these are natural gas plumes or methane plumes coming off of buildings. So this image in the middle, at the middle bottom, that's a methane plume that is supposed to be burned off. So this is at a processing facility, and you've seen those gas flares if you've ever driven up 80 through Vallejo. towards Sacramento, you go through a fuel processing plant, and oftentimes there's a burn off or a flame off going there, and that's a methane burn, a natural gas burn, and that if it's not burned, it's way worse than if it is burned. It's bad if it's burned, but it's way worse if it's not burned and just released. And so, other locations that they were looking at, this cloud in the upper right-hand picture, the cloud that this individual is walking up into, that's actually a methane cloud. So if there were a spark at that location, this person would certainly die. So we have way more undetected methane that's actually being shown to be way worse than the results of burning natural gas. So when we talk about trying to electrify buildings or get off of natural gas, we're actually doing it because systemically the infrastructure is failing, and the resulting leaking natural gas and methane is far worse than the actual residual CO2 when we burn it. So it's really important that we transition our buildings off and start cutting back this infrastructure, which we call sort of trimming the tree. The other piece in California specifically that makes electrification really appealing is our abundant resources for renewable energy. So these two maps, the one on the left is showing our wind resources. So you'll just notice this tremendous, into excellent, outstanding, and superb are generally how we describe the coastal sort of first 100 miles along the coast, and sort of right along the coast, and then sort of inland, up to sort of 20 to 50 miles in certain areas, and deeper in others. Phenomenal wind resources, and you can see that if you guys drive down 680 or go over the pass, you'll see sort of wind farms. Southern California actually has tremendous resources as well, especially when we get out into sort of the far desert area. If we overlaid that map on top of the map that we also have for solar resources, which is the image in the middle, California is really set up to have phenomenal PV production, solar electric production, as well as wind. And if you overlay those two maps together, the areas where we have less solar resources are actually areas where we have really great wind resources. And then in some cases, they actually double up. So if you look out at Riverside, and to the east of Riverside is sort of this amazing area of great energy resources for wind and solar. So we have these two complementary ideas. One is we have an infrastructure that's failing, that's creating a really bad carbon situation. And then we have abundant resources for renewable energy. So if we take those two things, then it really does make sense for buildings in California to start to look to entirely get off of natural gas and focus on electrification or electric-based systems. Now, Gail and I are going to talk next week more about mechanical systems, and so you'll have a better idea of what there are. I'll talk a little bit about them today, introduce some ideas. But the big idea is to try to move our buildings off of natural gas. If we look at the energy mix for California, so if any of you guys are ever interested in understanding how much of your energy comes from renewables for California, you can go to the CalISO site. It's the California Independent Service Operator. So they oversee our utilities, so PG&E, SoCal Edison, et cetera. CalISO oversees them in terms of managing the grid in California. The image on the left looks at just our historic trend for carbon intensity of our grid. So if you go back to 2014, is this top line. So every month you can see the carbon intensity of our electrical mix, and you can see over time for every year there was a little spike in 2018, but every year our carbon mix is getting smaller. So the amount of renewables on our grid is increasing, and the amount of natural gas used to make electricity is dropping. In the images up on the right, or top middle, you can actually see where our mix is for the state currently. So this is pretty recent. This is from December when I pulled this data. But right now, California gets almost 40% of their energy from renewable power, which is amazing. And then you can see the majority next fuel is natural gas. So that's the one we're really trying to reduce. And nuclear, coal, and other sort of make up a very small piece, and most of that nuclear is going away in the next 5 or so years. But you can see in the image on the far right, the vast majority of the renewable power on our grid is coming from PVs, so solar energy, which presents us with a challenge. So some of you may have heard about the duck curve and how we have a lot of electrical production in the middle of the day, and then it falls off. But you can start to see that actually in the daily data on the image on the right. And I just want to remind you, if you ever have an interest in going in deep with data, go to CalISO. You can pull any of this live information anytime you want. But you can see in this graph on the lower right-hand side that obviously in the morning hours we don't have a lot of solar, and then when the sun comes up, we start getting a lot of solar, and then it's great throughout the middle of the day, and then around 2 p.m. to 3 p.m. it starts to fall off again. And you guys know from solar geometry, the sun is starting to move over into the western sky at that point and getting lower and starting to set. So we have this really fast drop off of renewable energy, which means these other resources, so the natural gas plants, you can see having to spike at the same time. So to meet the total load need, as renewable energy starts to fall, we have to ramp up the other resources to compensate for that. And that is very carbon intensive time. So that those natural gas plants that are spiking to try to meet that load as everybody goes home from work, turns on all their lights, turns on all their equipment, they use a tremendous amount of energy. And the renewables are falling off at the same time. So you have this growth in demand and a fall off in supply of renewables. And so the natural gas plants have to make that up. And when they're doing that, they're typically relying on peaker plants that are more able to adjust their rate of climb. And those tend to be dirtier plants. And so that the carbon intensity of the grid around 4 p.m. to about 9 p.m. is actually turning into be a really big issue. If we actually start mapping the CO2 intensity for every hour, the state is trying to move towards much greener energy. So, as we're going towards more renewables, we're hoping that more of the hours of the day are low carbon. These graphs just sort of show that projection going through 2030. For each one of these little squares, it goes from midnight to midnight. Noon is down the middle, and left to right is January through December. So you can start to see that noontime in the summer months, really green power. We're getting very low carbon power, and it's actually has lower carbon emissions than burning natural gas. We still have issues in the middle of the night and in the wintertime for heating. So I'll just take the 2019 one and blow it up right here. But this is effectively looking at the carbon intensity of creating heat on site relative to burning natural gas. So in this graph, every hour, so we have hours from midnight or 0 to midnight on the left going down. So you see 12 noon is right in the middle. And then we have every month, January through December. You can see that if we were to use electric resistance heat, so think hair dryers, think strip heaters, maybe the little roll around space heater you might have in your apartment. If we use that with the current carbon mix of our grid for every hour, then the hours in red would use more carbon to heat than natural gas, while the areas in green would be more efficient. So you can see in the middle of the day, even from January all the way into August, the middle of the day, you could use electric resistance heat and be cleaner from a carbon standpoint than burning natural gas. And this would be to make hot water. This would be for space heating. It's really incredible that already with our grid mix the way it is today, many of the hours of the day actually have a lower carbon footprint even if you use electric resistance heat. Now, what happens if you use more efficient equipment? Well, this is that same graph where instead of using electric resistance heat, what if we used a heat pump? And we'll talk all about heat pumps next week. But the thing to remember today is that heat pumps tend to be around 3 times as efficient as electric resistance heat. So they have a coefficient of performance of around 3, somewhere as high as 5, sometimes as low as 1.5, but they tend to cluster around 3. So if we take the fact that a heat pump uses a third of the energy to, as an electric resistance toaster or a hair dryer, it uses a third of the energy to produce the same amount of heat. Well, if we take that and look at how much electricity you use and now compare it against the carbon intensity of the grid, as of today, all those green hours, all those green squares are hours where a heat pump is going to produce fewer carbon emissions than burning natural gas on site. And this includes all of the losses through the entire electrical grid. So there's losses between the transmission site. Each time there's a transformer, there's a little bit of loss. Getting power from the power plant or the solar farm all the way to your house, there's losses. But even with those losses, today, if you use a heat pump, all these hours of the year are going to be more carbon efficient than burning natural gas. So this is why, as a policy standpoint, we're so interested in getting buildings off of gas, because today, using today's technology, nothing fancy, using today's technology, we can be way, way, way more sustainable and low carbon than if we used natural gas and burned it. And this doesn't even include the leakage. So this is just the combustion CO2 emissions. This does not include the methane leaks that I just talked about a few minutes ago. If we had included those, the entire graph would be green. So how are we doing this transition? What are we starting to see in the marketplace? Now, again, I'm not going to go into too much detail with each of these systems because we're going to talk about them next week. But we're seeing a big push to get rid of furnaces, get rid of the old furnaces that you might have in a closet or in a basement, and switch to heat pumps. So these could be mini split heat pumps. They could be VRF, variable refrigerant flow heat pumps. They could still look a lot like this image on the left, but they almost all have an outdoor unit, which looks kind of like your old air conditioners. But a heat pump is essentially an air conditioner that can flip, and it can do heating or cooling, depending on the season. So we're seeing a big push to get rid of furnaces. On big commercial buildings, we're seeing a big push to go to what we call air to water heat pumps. And so these systems are effectively taking air from outside, they run it through a heat exchanger, they steal that heat out of the air, they compress it, and they put it into water. So we can pair those systems with all sorts of fan coils, chilled beams, all sorts of fun stuff that we're going to talk about next week. We can pair those air to water heat pumps with radiant, so we can do radiant heating and cooling. One of my favorite systems. So a lot of options. So there's technology already ready today to actually help with that transition. One of the biggest energy users in the state is our domestic hot water systems. And so if you look at all the apartment buildings and multifamily buildings that are under construction or being built, a lot of them have sort of this image on the left, these old school gas-fired boilers with some storage tanks. When we look at how one of these systems is actually piped in a building, they've got this big system in the basement producing all this hot water. Well, in real life, there's quite a bit of loss coming from the actual system. There's loss in all the piping going around your building, all the heat going out of your building. You lose about a third of the energy just in the piping that's going around. And so by the time you've burned all this natural gas, you only end up getting about 35% of the heat that you made delivered to your faucet. So what you shower with, what you wash your hands with, that water total is only about 30% of the water you heated. There's a lot of losses in those systems. And so as we look to do low carbon designs, there's a lot of emphasis on trying to change the way that we deliver hot water in buildings and the systems that we're using to make it. So you're going to see a rapid change in the market to switch traditional water heaters, gas-fired water heaters, with heat pump water heaters. And they come in all sorts of flavors. The image on the left is sort of for a residential house. It's what we would call a ducted heat pump water heater. So that top third of the tank is actually a little heat pump in there. And it's taking air from outside, stealing the heat from it, and then dumping the cold air, often in the attic or in back outside. The image on the left is a CO2 heat pump. So it actually uses carbon dioxide as the refrigerant, which is really exciting. But that unit could go sit outside and the tank could be inside. And then in our big commercial buildings, we're seeing heat pumps at scale. So these are large scale industrial air to water heat pumps meant specifically for making hot water for apartment buildings. Now, it's a little bit in the weeds, but hot water systems or heat pumps have one area that they have a weakness compared to a gas-fired boiler. And that is because they're trying to steal heat from the air, they struggle when the air gets cold. And so you can see on these graphs here, the efficiency of the unit as the outside air drops, so as the air goes down to say towards 40 degrees, you can see that the efficiency of many of these units drops down to 3 or maybe even lower. And so we have to make sure that we size a system large enough to account for that lower energy production. The other downside of the systems is, again, as it gets colder, the amount of heat that they can actually make also drops. So it's really important when we're sizing these systems to actually look at climate data. And so a lot of plumbing engineers aren't used to looking at climate data to design their systems. They just pick a boiler and it burns. But when we're doing heat pump systems, it's really important to design around your actual climate. So there's a question about whether instant hot water heaters are similar to heat pumps. They typically are not. So there's two types of instantaneous water heaters or tankless water heaters or point of use water heaters. Those are sort of the three names that we use for those. There's a gas variety and there's an electric variety. The electric ones are just using electric resistance. So it's kind of like, I know it sounds weird, but it's kind of like using a hairdryer to heat water, except that instead of blowing hot air, there's electric coil wrapped around piping and it heats the water directly. So that would only have a COP of 1. So we try not to use those. And lots of folks moved over to instant water heaters with gas, because everybody in the market told them to about 5 years ago. Well, now we're realizing that those carbon emissions are really bad, or more than we thought. And so we're trying to get people to move off of instantaneous water heaters and go to heat pump styles. So one of the really big things on heat pump water heating is whether you can actually use them in cold climates. And so there are some heat pumps that are actually designed for cold climates. The one in the middle here, this guy right here, this is a CO2 heat pump. CO2 heat pumps actually love being in cold environments. They have what we call a really high lift. They can take very cold air and still extract a lot of heat out of it and make the air really, really cold that leaves. But they can work down into, without losing too much efficiency, down to about 10 degrees Fahrenheit, so pretty cold. After that, they kind of drop off a little bit, so you would need to size them a bigger one. But for most areas in the United States, if you were in a cold climate, you'd be wanting to look at a CO2 split heat pump because they're really efficient, even in cold weather. So this is, so one of the things though that we want to start thinking about, so relative to this efficiency chart, so we saw that below 60 degrees, the efficiency of the equipment starts to drop, its capacity starts to drop. Well, the next piece that we're working on right now is actually applying that same data onto this graph. So I said earlier that if I had an average COP of about 3, this is what the new carbon intensity map would look like for making hot water or space heating. But notice that if I'm trying to heat a building, I'm often trying to do it in these hours. So January, December, January, February, midnight to 5 a.m. Those are the hours that I'm generally need to provide heat. And those are the same hours where a heat pump may be less efficient. And so from an engineering standpoint, we're working really hard to look at what we call load shifting and trying to move energy around when we use it so that our heat pumps can operate during these really prime middle hours and store energy for later use in the evening. I'll talk about that a little bit more, and we'll definitely talk about that more next week. So one other piece of this is that because we're crazy engineers, we ask, well, if the air outside is really cold, are there other options that we can use to get really good source energy? So a heat pump really wants, if I'm trying to heat something with a heat pump, it really wants to pull heat from somewhere that's already warm. Well, if it's cold outside, are there any areas that could be a better source of heat? Well, there happens to be. If you think about where water leaves your building or energy leaves your building, one of the really warm ways that it leaves is from your shower water and your waste. So buildings produce a tremendous amount of waste coming out of the sewer. So all that shower water, just think about all the energy you used to make 120-degree water. We blend it down to 104 degrees. It comes out of your shower. It's toasty warm. It steams up everything. And it goes down the drain at 75 degrees. Well, now you have this really nice flow of 75-degree water leaving your building that goes nowhere. That heat is lost to the ground in the sewer lines as it makes its way to the sewage plant. So there are systems on the market now that actually let us steal the heat from that waste. I know it sounds kind of gross because it's all sorts of stuff in that waste, but we've definitely done it. We have a project I'll show you in a little bit. And there's a really high amount of elegance to the system, because if you think about when a building is calling for hot water, like is in the morning when you're showering, and then in the evening when some people are showering. Hopefully, I know you guys are in college, and definitely I have not been showering as much as I used to while I've been in quarantine. But there's a really nice balance between when hot water is available coming out of your sewer and when you need hot water, because those things are happening at the same time. So there's a couple of systems on the market that essentially take all of your waste going into a tank. We then use a system to pump out that waste, and it goes through what we call a macerator, which is kind of a gross thing, but think of it as a blender for sewage. So it chops up everything, cuts up everything into a slurry, runs that through a heat exchanger, and then dumps it back into the sewer. The heat pump is just stealing the heat from that slurry in the heat exchanger. So there's the poo water, if you will, never comes close to the domestic hot water. There's a heat pump in between. But this, in the image in the sort of bottom left, this white box guy is from a company called International Wastewater Systems. And that system has the macerator built in and the heat pump. So it steals the heat from your waste and then uses it to charge a tank, to fill a tank with hot water, or to keep heating the tank with hot water. So as you're showering and producing a lot of hot water, it's using that heat to make new hot water for the shower. So really elegant system. There's some images on the right. They're not terribly big, but really exciting systems. And they don't have to be used just for individual buildings. So that same sewage heat exchange system is used at the Vancouver Olympic Village. So the entire residential portion of the Olympic Village was actually heated from wastewater heat pumps. So kind of exciting. And the reason that it's exciting for me from an energy efficiency standpoint is that when we talked about air source heat pumps, their COP, their efficiency is about 3. So you get 3 times as much energy as you put into the system. These systems, because they're pulling heat from an area that's already really warm, they tend to have a COP higher than 4. So 4 to 5, even sometimes upwards of 6, which means you can get, say, 5 times as much energy produced as the electricity that the system uses. Because it's not trying to burn something, it's actually just stealing heat from one location, compressing it, and putting it somewhere else. And so the power of a heat pump pulling from a really rich source, like wastewater, is that there's a lot of heat there to steal. And so the efficiency of the heat pump goes up dramatically. So these systems can actually produce 5 times as much heat as the actual electricity being used to power the heat pump. Something pretty exciting for us is we actually use this in a strategy in Washington, D.C. So this is the building in the middle, sort of curvilinear, sort of greenish glass face, is the new DC water headquarters. And so this is a building that literally holds the water department, so all the staff for the water department for Washington, D.C. And it happened to be located next to a pumping station for wastewater. And it's on its way to go to a treatment plant. And this is there's a big pipe. This is a very low point. As you can see, we're right next to the river. There's all the sewage is coming here, it's getting collected, and it gets pumped to the sewage treatment plant. And the actual pressurized sewage line is over 20 inches. So you could fit inside the sewage line. So it's a lot of waste. But for us, that meant, well, if we have to build a building here and there happens to already be a very large waste line that's pressurized, we wanted to take advantage of that. And we had been doing some research in wastewater heat exchanger systems. And so this is the first building in the United States that uses wastewater heat pumps to do all the heating and cooling for the building. So there's no cooling tower on this project. There's no big equipment. It's actually a pretty small heat pump in the basement that provides all the heating and cooling by doing that same system where we actually extract waste from that sewer line, macerate it, run it through a heat exchanger, and then return it to the sewer. And then our heat pump is stealing heat from that heat exchanger or cold. It either pulls heat or pushes heat into the waste. And that's actually providing all the heating and cooling for project. And DC can get cold, and DC can get really hot and humid. And so there's actually a lot of heating load and a lot of cooling load. And the system is a really sort of elegant, low-cost system that is exceptionally efficient year-round. So pretty exciting for us. And we're starting to deploy these systems now and look at them, especially for multifamily buildings, because there's so much hot water used in a multifamily building. It's a really great opportunity for us to make high efficiency hot water. Oh, so speaking of poop, it's quiz time. We're going to jump over to the quiz. So hopefully everybody is going to get situated. We're going to give you a couple minutes to make sure that you can get over to B course. So you're going to go over to the syllabus, week 12, April 15th. So this would be quiz 6. And just like last time, we're going to do 12 minutes total for the quiz. And I will give you a warning at the halfway point, and I'll also give you about a 1 minute warning before we get to the end. So we'll still give everyone a chance to navigate over there before we open the quiz.
And Steph, my understanding is while they're taking the quiz, they're also there's a timer that shows up for them.
Perfect.
Carrie told me that. So they have multiple ways to keep track of time. And then Carrie, I know you've gotten yourself over there.
Yep, I am unlocking the quiz now.
Okay, call out when unlocked.
The quiz is now open.
All right, everybody, good luck.
Gail, did you want to quick go over the
Yeah.
answers?
Yep. So the answer to this one is false. The red list is a much more restrictive list of materials that are banned than those other certifications. The answer to this is glass. The answer to this is false. The transparency movement refers to declarations about what's in building materials so we can make informed choices that support the health of people in the building. It's not about views through the skin. The answer to this is true. The answer to this is that this refers to California's building energy efficiency standards. And finally, the answer to this is natural ventilation.
Super.
Okay, and I see a question in the chat about releasing quiz questions. Historically, we don't post the quizzes or exams, but what we do is we've put several exams and solutions on B courses under files, and you can use those for studying. And you might find that many of the questions on the quizzes actually come from them.
Awesome. Thanks, Gail. Oh, hold on, Gail, one quick question. The first one.
Okay, Maya, the first one was about red lists, and the answer was false, that the red list in Living Building Challenge is much more restrictive.
Yep.
Oh, sorry, Stet.
Yeah, go ahead.
I just wanted to let everyone know, I think there was some confusion about the time limit on the quiz, locking the quiz. I just sent a message in the chat, so you can take a look at that. But we're just making sure the 12 minutes is for everyone. Once you open the quiz, you have 12 minutes, and then it will time you out if you haven't completed at that point. It will auto submit if you don't click submit, so your score will be recorded as long as you selected an answer for the last question. And when we say we're locking the quiz, that's just so no one can start the quiz once we go over solutions.
Thank you.
Great. Awesome. So we're going to jump back in. I wanted to use this second section to sort of walk through some example projects so that you don't think that this is just crazy Stet in the corner making all electric buildings, although a lot of these are my projects I worked on, but that every building type, there's a strategy to electrify. So in the South Bay, there's a really great group called Sharp Development. I've been working with them for years, doing net zero energy retrofits of existing buildings. So these are existing like tilt-up kind of gross 1970s buildings that we've been doing deep energy efficiency upgrades, doing really good envelopes upgrades, and then converting them to all electric net zero energy. So this was a project called Indio down there with the architects were RMW, engineers were Integral Group. Currently, the building on the right is up at Lawrence Berkeley Lab, so just up the hill from Worcester. It is a integrated genomics lab, IGB, and so it's a heavy duty, heavy science, heavy wet chemistry lab. And that building is all electric with using a cooling tower and chillers for cooling and air source heat pumps for heating. And it's a phenomenal project that just opened. It's a Smith Group project, so I get to reference it. But then immediately next to it, so the image on the left is right next door, and that is a building that we have in design right now, and it's the new called BioEpic, and it's a biological research lab. So very complex, again, wet chemistry, wet biology, a lot of very fume hood intensive, so a really energy intensive building. But that building is also going to be all electric and be able to source 100% renewable power. We won't be able to fit all the PVs on the building, but if they source from a power purchase agreement, that building could also be carbon neutral from the production side. So you can all over the place. You can be very simple one-story buildings to very complex labs. I know that I shouldn't talk about Stanford, like boo, but they have a beautiful central plant that just opened a couple years ago, actually maybe just 2 years ago now, that is an all-electric heat recovery chiller central plant with a tremendous amount of thermal energy storage. Huge hot and chilled water tanks sit right behind this plant. But it's a beautiful building. It was done by ZGF and AEI, so they're competitors of ours, but beautiful building, beautiful central plant, and all electric. And so they've been converting their entire campus off of steam, which uses natural gas boilers. So a really phenomenal job at that campus, and I would hope Berkeley can find the funding to do something similar. So when we talk about electrification, there's always this worry of what happens if everybody does it. Can the electrical grid still function? And the beauty of thermal storage, so when we talk about Stanford's plant, is this using this tremendous amount of stored hot water and still stored chilled water, is that it gives us flexibility about when we use power. And this is not a new concept. We've been doing energy storage for a long time, and the state has really incentivized it. But it becomes even more important if we start to look at trying to transition the entire building stock in California over to all electric systems. Because if everybody used power right at the same time and everything was all electric, the grid would struggle. And so thermal storage, battery storage, both become very efficient tools to help us manage our load. So the images on the right are just talking about why efficiency matters so much when we talk about electrification. So if we have a base case or a base load building has a certain shape to it, one of the big things that we wanted to still work on is sort of shaving those peak hours, not using too much power when everyone else wants to use power, if we can all bring our power down. The biggest tool in our toolbox is still efficiency. So conservation and efficiency measures are still the biggest thing that we want to do, even if we could go all electric. And that's not necessarily for a carbon story, but it's for a reduction in peak loads on the entire grid. So all the stuff that we're doing in 140 is actually really important for the good envelope, good window, whole building heat transfer, daylighting. All those pieces are really important to actually do the efficiency piece. If we combine efficiency with peak load management, then we get the holy grail of being able to move our energy use to a time of day when it's both carbon, reduced carbon, but also when it helps balance the load on the grid. So this is some really exciting work, and I'll talk a little bit about this more next week, but this is actually coming out of the Center for the Built Environment, which is a tremendous research group at Berkeley that Gail actually leads. This is a study coming out of some research on mass radiant floors. And when we talk about load shifting, often the conversation is all about batteries. Like everybody wants to talk about batteries. How can I put more batteries, battery technology? One of the really exciting research ideas coming from Paul and the team at the CBE is looking at the ability for mass radiant buildings to actually shift when we actually need to provide cold water into the slab to still provide comfort. And what the research is showing is that if we just picked, say 9 hours and we provided chilled water to that slab for 9 hours, we can actually move when we do it almost any time throughout the day and still maintain comfort within the space, because the inherent lag in the slab, the thermal storage of that slab actually gives us a lot of flexibility. And so one of the most exciting things that we're seeing on the engineering side is actually utilizing our buildings themselves and the materials in the buildings as this load shifting component so that we can match when our chillers or heat pumps work with the carbon intensity to the grid. And so that's a lot of the work that I'm doing right now, is trying to match these really great low energy systems that we've always loved and pairing them with sort of carbon intensity. So a question from Michelle is, can we see this in all climates? Mass radiant heating and cooling paired with a good envelope works in nearly every climate. because you can deal with humidity on the ventilation side. And so assuming you have a good envelope, yes, you should be able to do this. We're doing it in crazy climate zones. The downside is if you have a building with a really bad envelope. So imagine a building in Abu Dhabi that's 100% glass with just dual pane glass, no shading, then you will likely exceed the cooling capacity of a radiant slab. So we can't ever think about these systems independently. It's all together. So a building envelope and a mechanical system have to pair well. But that load shifting capacity is very flexible in mass buildings. So this is some really exciting work that we're loving that Berkeley is doing, because we're taking learning from it and trying to apply it to use these same load shifting strategies to actually match with the carbon intensity of the grid. So that's our ultimate goal, is to actually be able to take our loads, shift them around so that we can run our equipment during these green hours. We want all of our heating and cooling equipment to actually run when the carbon and the grid mix is at its lowest. So load shifting is really important. So thermal storage is going to be really important, whether that's in the mass lab or stored water, but also battery systems are going to be important. And we are focusing a lot on them. Which brings me to one of the questions we get a lot about electrification is what happens when the power goes out? All of us have experienced the preemptive power safety shutoffs from PG&E with the wildfires last year. And so that's a really big concern. But to give you guys an idea, power has typically come on, electrical power has typically come on post-disaster within 3 days, with like 80% of people getting power back within 24 hours. In an earthquake, it typically takes us about 6 months to get gas service back on to all users, because they have to go house to house and check pilot lights before they can turn more network on for fear of explosion. So gas is actually far less resilient than electricity. And we know that those power shutoffs affect clients in different ways. So you have the actual outage period, which is bad. But if you think about for hospitals or other places that schedule, if you don't know when your power is coming back on, you can't schedule out in the future. And so resiliency and electrification need to work hand in hand. But there has to be another mechanism. So what we do is actually a lot of analysis around our clients' utility bills when we start thinking about electrification and energy storage. There's a little thing called a demand charge. It's not little. It can be about half of the bill for a large, say, hospital or lab, upwards of 40% of their cost of power. And that demand charge is shown kind of on the graph on the left. It's every 15 minutes throughout a month, they just check what increment did you use the most power, and then they charge you a ton of money for that amount. And if you can flatten that out and get rid of those spikes in your energy use, you can often cut the energy bill of a large entity by 30%, which is huge. I mean, we're talking hundreds of thousands of dollars of savings a year for like a hospital. And one great way to do that is thermal energy storage. Another really phenomenal way is to actually use battery backup. So PVs plus battery. The batteries can help us do that demand charge manipulation, but if we combine on-site PVs with batteries, all of a sudden we have a resiliency story, because we can stand alone, we can microgrid our building, and it can act for days by storing enough power to get through the night. So if we can combine PV power plus batteries, PV power plus batteries plus thermal storage in the building, all of a sudden you're developing a building that could operate for potentially weeks at a time, independent of what's happening on the grid. So there's a very strong resiliency story that's in parallel with an idea about electrification. So electrification plus storage gives us that resilience flexibility that we're looking for in our buildings. The really nice thing is, because that same system can provide that demand charge manipulation, that system can, for the entire year, provide us with a really positive cash flow rate. So we typically see returns on investment right now for microgrids less than 10 years, which is phenomenal. And that's just manipulating the demand charge. That's not even looking at the reduced cost of power. But that same system for 99% of the year can be giving you this really great financial return. And in the event of an emergency, that same system can give you that resilience. So it can give you that preparedness for emergency shutoffs. It can give you extra capacity if the whole world is burning down. And so, and you can't say that for natural gas, because natural gas will get shut down in an earthquake. Natural gas often gets shut down in wildfire areas. And so there is no real, and you don't want to store large volumes of gas on your building. And so we're really seeing this trifecta of on-site renewables, storage, load flexibility within the building. It's giving us annual benefit, and it's giving a tremendous story around resilience that we really need in California. So one of the tools, I just wanted to share it with you. If any of you guys are super interested in microgrids and energy modeling, I know I did a whole lecture on different energy modeling tools, but there's a program called Homer, which is something optimization of microgrid energy resources or something. I forget the name, but it's really cute because it's Homer. We can model full microgrids now with wind energy, solar energy, biogas, which I think is not good, generators. All of those pieces can fit into the system, and we can include all the parameters around lifespan of the components. So there's a question about lifespan of batteries. Typically, we're seeing about 14 years for batteries before they start to get down to about 80% charge. They're still very usable, but they might go into a second life of home energy storage after that point. But we can model all the replacement costs, the carbon piece, and the resiliency piece. So the really nice thing about Homer is that you can put in there that you would like to design your system around an unplanned power outage that lasts 4 days, 5 days, and it will help us size a system of PVs and batteries and generators that can actually live through that period, but then show the financial benefits throughout the year. So really exciting tools are on the horizon. We're using them now. And I can tell all of you that when you guys get out into the marketplace and are working in jobs, there's already going to be a groundswell around electrification of buildings and getting off of natural gas completely. So renewable power is going to be really important, but also getting your buildings to be really efficient so that they're grid friendly or grid optimal is a really great program that gauges that. So yeah, that's my pitch for getting all of our buildings off of natural gas and pushing towards a renewable future, but making sure we do it in a really smart way that takes our systems and matches them with when the grid in California has its lowest carbon density. So that's it.
That's a great lecture, Stet. I certainly learned a lot, and we've got some time. So if people want to either unmute and ask Stet questions, that would be lovely. You can also type it into the chat. I had a question, Stet. I mean, you made a great argument for why all of this is the direction we should go. What's been the biggest pushbacks that you've had to deal with, either dealing with the city of Berkeley or in other arenas?
The biggest impediment actually is one, unknown. A lot of folks don't know about certain technologies around electrification, especially cooking. People get super nervous when you say you want to take away their natural gas for cooking, because in their mind, electric cooking are those old like spiral electric cooking things that were awful, and I burn food all the time with them. Now we've moved to what's called induction cooktops, which use magnetic energy to heat the pan itself instead of sort of resistance cooking. A lot easier to control, a lot more efficient. So cooking has been the big impediment, and both there locally at home and also for commercial food vendors, restaurants. The other piece is trying to grapple with renovations. And so one of the things, I'm part of the San Francisco Mayor Breed's task force on decarbonization. And one of the things that we're struggling with right now is that's great for new construction. We think we should totally do it. New construction, gas-free, all electric. But if you look at a city, 95% of the building stock is already there. And so how do we do a just and equitable transition off of natural gas in cities and still be able to operate within the infrastructure that's there? So the electrical infrastructure is already sort of strained in some cities. How do we start to do a phased approach to electrification for existing buildings? That's probably the hardest nugget that we're all working on right now. And then just one other sort of thing to keep in mind, especially around equity, is that gas prices are going to skyrocket in the next 4 years because of all the infrastructure upgrades that the state is requiring. Gas suppliers, so PG&E, SoCalGas, they're all passing they're going to pass that cost on to ratepayers. And so they're anticipating gas prices are going to jump 40% in the next 4 years, which has a huge equity impact on low-income communities. And so there's a lot of work locally with energy agencies to try to set up plans to help electrify and retrofit low-income communities' homes over to all electric with PV, because it can help dramatically insulate folks from price spikes.
Thank you.
Yeah.
Thank you.
Any other questions?
Thank you.
Super.
Okay. Well, we'll wrap up 2 minutes early then.
My gift to you.
Yeah. GSI team, take 5 and then check into our GSI meeting as soon as you can. We've got a big agenda, and see you all soon.
Okay. Thanks, everyone.